Hello everyone and welcome. My name is Jason Kregerson, and this video is going to be Introduction to Solving First-Order Linear Systems with Constant Coefficients. In this process, we're going to review the process that we use to solve higher-order differential equations with constant coefficients and relate that to our new process for solving systems. Let's look at a table. This table has three columns. The first column describes the general process steps. The second, we'll see how we have previously applied those steps to solving higher order differential equations. And the third column will take those same steps and apply them to our systems. So, if we look at column 2, if we look at the differential equation x double prime plus 2x prime minus 3x equals 0, we already know how to solve that. Our first step was to make this assumption that our solution had the form e to the rt. And based on that assumption, we are able to generate our auxiliary equation. We made our assumption, then we calculated the derivative, and we calculated the second derivative. And we plugged those into the differential equation, and we factored out our e to the rt, and the result was this auxiliary equation. But once we've gone through that process, we could really just jump to our auxiliary equation. And that auxiliary equation, if we were able to solve that, we'd be able to find the parameter r that we need to make our assumption an actual valid solution. So the auxiliary equation is this thing we solve to find r such that our solution is e to the rt. Now, how do we solve our auxiliary equation? Well, we either factored it or we used the quadratic formula. Then we'd find our r's, and then we could form our general solution as the linear combination of the solutions we got for our different r values. So that's our process that we've already gone through for solving higher order differential equation. We assumed a form of our solution, we generated an equation, which we were able to solve to find our parameters, and we formed our general solution. Now, as we look to linear systems, first order linear systems of differential equations, we're going to make a different assumption. Our system has this general form here where we're using vector notation. So it's the vector u prime equals the matrix A times the vector u. But that really has the feel of a first order differential equation. And so it looks like the derivative of some function equals a constant times that function. That really reminds us of exponentials. So it seems reasonable to assume that our solution might look like some constant, or maybe in this case a constant vector, times e to the some number, some constant I'll call lambda, t. So we're basically assuming our solution looks like a vector of constants times e to some number t. Now, based on that assumption, we're going to want to generate an equation. And we'll go through that same process we did before. We're going to take the derivative. If I take the derivative of my vector u, I will get lambda times the vector x e to the lambda t. And if I plug those into my differential equation, if I take my differential equation, I just write it kind of in the opposite direction to look like this, and then I plug in the different pieces, well, I'll have the matrix A times u, which is x e to the lambda t, and that should be equal to u prime, which is lambda x vector e to the lambda t, and then I notice I could divide through by my e to the lambda t's, and the result is going to be a times x equals lambda x. And we might recognize this as the eigenvalue problem. So in our column 2, for a higher order differential equation, we made our assumption that our solution looked like e to the rt, and the result was a polynomial that we could then solve to find our parameters. In a system, we make our assumption that u is equal to some vector times e to the lambda t, and our assumption leads us to the eigenvalue problem. So if we can find the eigenvalues and vectors of the matrix A, we will then know the parameters we need to solve our problem. So how do we find those eigenvalues and eigenvectors? Well, recall that to find our eigenvalues, we'll look at the determinant of A minus lambda I. We'll set that equal to 0, and we'll solve for our eigenvalues. Once we have our eigenvalues, we'll then solve the homogeneous matrix equation, A minus lambda I times x equals 0, and we'll solve that for our eigenvectors. At that point, we'll know what lambda and x are, so we'll have a eigenpair, an eigenvalue paired with its eigenvector. And then we can use those to form our general solution. I will know that one solution will look like the first eigenvector e to the first eigenvalue t. The second solution will look like the other eigenvector e to the other eigenvalue t. And then I can form my general solution as shown. So now we have the general steps. We basically need to find the eigenvalues, eigenvectors of the matrix A, and then we can use those to form our general solution. Now let's see this in actual practice. So here's my system. Here's my system of first order linear differential equation. And I've already rewritten the matrix vector form. And so I make my initial assumption that a solution looks like some vector e to the lambda t. And now I have to calculate my eigenpairs. So step one is to solve the determinant of a minus lambda I equals 0 for my eigenvalues. So I will subtract lambda on the diagonals, calculate the determinant, which in this case would be 2 minus lambda squared minus 1. I'll expand that to get 4 minus 4 lambda plus lambda squared minus 1, which in this case should give me lambda squared minus 4 lambda plus 3. And the question is, when is that equal to 0? I'll factor that to be lambda minus 3 and lambda minus 1, and that is equal to 0 when lambda is equal to 1 and 3. So I've been able to calculate my eigenvalues. Next, I have to find my eigenvectors. So then I'll say if lambda equals 1, for instance, I then need to solve the homogeneous matrix equation A minus lambda I times my eigenvector equals 0. So I subtract lambda on the diagonal. So 2 minus 1 is 1. I'll end up with this matrix, this equation here, which I'll generate the augmented matrix, and I'll have to do my row reduction. When I do my row reduction, I'm basically going to take row 2 minus row 1, and it will row reduce to this. From here, I'll write out the associated equations. x1 is equal to negative x2. x2 is my free variable. And I can write my solution in parametric vector form to be this. And so from here, I can see my first eigenpair is when lambda equals 1, the associated eigenvector is negative 1, 1. So there's my first eigenpair. I'll do the same thing with my second eigenvalue. If lambda is equal to 3, I will then subtract 3 on the diagonals to get negative 1, 1, 1 and negative 1 augmented with 0. I'll do my row reduction here. I'll take row 2 plus row 1. That will give me a row of all zeros. I'll multiply the first row by negative 1 to get this value. Now I'm in row reduced echelon form. I'll write out my associated equations. x2 is my free variable. My solution in parametric vector form will be this. So it looks like my second eigenpair is going to be when lambda 2 is equal to 3, then my second eigenvector will be 1, 1. So now I have my two eigenpairs. Remember, my assumption was that a solution looks like the vector times e to the lambda t. So that means my first solution should look like my first eigenvector, negative 1, 1, times e to the 1 times t. My second solution should look like my other eigenvector, e to the 3t, and my general solution should look like c1, negative 1, 1, e to the t, plus c2, 1, 1, e to the 3t, a linear combination of my two solutions. All right, so what we've seen here is I basically have this system of first order linear differential equations. I generate the associated matrix, I find the eigenvalues, eigenvectors, and those let me form my general solution. All right, that concludes this video. Thank you very much.